Hello, so in this video we will talk about the basics of a special kind of graph which is known as a tree. Okay, so by definition there are many alternative definitions, by the way. So two of the definitions are given here. Uh, One is that a connected graph with no simple cycle is a tree. Okay, and also a connected graph whose every edge is an articulation point of that graph is also a tree. Another alternate definition you will see in text is a connected graph with n vertices and n minus 1 edges. So n vertices and n minus 1 edges. This is also a tree. It has to be connected. Okay. And if we have a graph with no simple cycle that is not connected, that is called a forest. So every component of that graph is a tree. Okay. And typically the type of tree used in applications is a rooted tree. So a rooted tree is that one of the vertices is designated as a root, and all other vertices are directed away from the root. So it's kind of a directed graph, but the arrows are not shown. It's always root on the top and the other edges on the bottom. Okay, on below it. Okay, and different choices for root leads to different rooted trees, and we will see an example for that shortly. And some more definitions without going through it. I mean, these are just common sense kind of definitions. um, I will just use two of them, or vertex. Just talk about two of them. So this says that a vertex is a leaf if it has no children, and vertices that have children are called internal vertices. Okay, so now we talk about a full M-array tree. So M-array tree is a rooted tree such that each internal vertex has no more than m children. Okay, and when m is equal to 2, the tree is called a binary tree. Okay, which is very popular. And if each internal vertex has exactly m vertices, then it is said to be a full M-array tree. Okay, and the level of the vertex is the length of its unique path from the root. Okay, so every vertex from the root constitutes a unique path in a tree. Okay, and the height of a tree is the length of the longest path from root to any vertex. And a rooted emissary tree is balanced if each leaf has a level of h or h minus 1. Okay, and if every leaf has the same level, then the tree is complete. So these are just definitions. I mean, once you see a tree, you can easily see whether a tree is satisfying these balanced or complete or full um conditions or not. Okay, but what we are really interested in is that for an M-array tree with I internal vertices, the number of vertices n is given by m times I plus 1. So the proof of this goes like this. So we have to think about how many vertices are children of internal vertices. So how many vertices are children of internal vertices? All of them except the root, correct? So all except root. Okay, and how many internal vertices are there? Internal vertices are I. So how many, each vertex has how many children? M children, M-array tree. Okay, so it should be full M-array tree, I would say. So except root, this should be full. So this means Mi total children plus the root. So Mi plus 1 is the total number of vertices. Okay. And similarly, for a full M-array tree with I vertices and L leaves and with I internal vertices, N vertices, and L leaves, only one of these need to be known and other two can be found. So all we have to do is we have to use this equation and this equation. How does this equation come into being? This says that number of vertices is the sum of internal vertices plus vertices which are not internal vertices, and only the vertices which are leaves, they are not internal vertices. So if one of these three is known, we can use these two equations to find the number of vertices and the number of internal vertices or number of leaves. Okay, for a full M-array tree. Okay, now let's go back to a question here. Okay, so maximum number of leaves for an M-array tree of height h, this satisfies m to the h. Okay, so how do we approach this? So we use induction here. Induction on H. So what is our base step? Base step is H is equal to 1. When H is equal to 1, we have a tree like this. We have like this, like this, and like this. So this is my root and this is my level 1. So this is my H1. So this is, since this is an emery tree, so how many leaves can be there? There can be m leaves because the root can only have m children. Okay, so this means base step is, so number of leaves may be L. This is less than or equal to m to the 1, which is equal to m. Okay, now inductive step. So for inductive step, we say that assume let all trees with height of k minus 1 have number of leaves less than or equal to m to the k plus k minus 1. Okay, so this is my inductive hypothesis. So inductive hypothesis. So now what we do, we construct a height k tree and remove edges from root to level 1 vertices. So what does it mean? It means that we have this kind of a tree. So we have this kind of a tree, and then we remove all of them, all of these edges. So we remove this guy, remove this guy, remove this guy. So then this means this will lead to a maximum of m trees with height k minus 1. And we all know that for these number of leaves, so for those we have L less than m to the k minus 1. And how many of them are there? Because root has a maximum of m edges or m children. So this means that for, so this, if this tree is T, so for T, L is less than m times m to the k minus 1, which is equal to m to the k. Okay, so we have proved the inductive hypothesis. So this means that for a maximum number of leaves, for an emery tree of height h is always upper bounded by m to the h. Okay, so this is another example of induction here. Okay, now let's go to another question. Now we have to generate non-isomorphic trees with 5 vertices. Okay, so there are two cases, rooted and unrooted. Which one do you think will have more options? Any guesses? Rooted will have more options because for root we have 2 degrees of freedom. For unrooted we can only have degree sequence is something which determines how many non-isomorphic trees I can have. But for rooted trees I have degree sequence and the selection of root as my choice. Okay, so let's start with unrooted trees now. So for unrooted trees we have, remember, with 5 vertices. So we can have this guy, or we can have this guy, or we can have this guy. Okay, so a viewer can see that these are the only options. Every other option with 5 vertices and 4 edges and connected without a cycle will lead to what? Will lead to one of these forms. Okay, so this is unrooted. Now we talk about rooted here. So let's see how many we can make from here. So first of all, we can just make the first one as root. Then we can make the second one as root. Okay. Then we can make the third one as root. But if you make the fourth one as root, it will be similar to this one. If you make the fifth one as root, it will be similar to this one. So this is for this guy. Now let's say this guy. Okay, so for this guy, we have, if we make, for example, this guy the root, then we get something like this. And then we can get something like this. And then we can get something like this. And then we can get something like this. Now you can appreciate that every version of this is this guy. Okay? And this guy is just already, in rooted form. And the other option from this is this guy. If you make this first one the root, you will get this. If you make any one of them the root, you will get like this. Okay, so now you can actually appreciate that all of them are non-isomorphic to each other. Some of them have different heights, some of them have different children forms, some of them have number of siblings different or something like that. Okay. Okay, for example, if you check this guy and this guy, this has 2 levels and this has 3 levels, so clearly non-isomorphic. This guy has different scheme of children for the vertices here. Okay, and similarly you can check this one. These one are clearly non-isomorphic because they have different heights. And similarly this guy is non-isomorphic to every other because this has 2 height of 2 and these ones have height of 3. This is height of 2, but this is clearly different from this because this has 2 vertices, 2 children from the root. Okay, so this is how we form different isomorphic or isomorphic trees from a given number of vertices and uh, in the form of rooted and unrooted versions. Okay, so this is it about the rooted trees and unrooted trees and some definitions about the trees and some theorems and how we can find some different properties of trees and how we can use induction to prove some properties for trees. Hope it was easy to understand and thanks for watching. Hope you liked the video.